Hello, everyone, and welcome to my talk. I'm going to talk about distributed approximation for maximum weight independent set. This is a joint work with Ken-ichi Kawarabayashi, Aaron Schild, and Gregory Schwartzman. In this work, we consider the well-known CONGEST model. So in this model, we have a network of n nodes. We have synchronized communication rounds. And in each round, each node can send an O of log n bit message to each of its neighbors. The goal in the CONGEST model is to compute some function of the network while minimizing the number of communication rounds. In this work, we consider the complexity of finding an approximation to maximum weight independent set in the CONGEST model. So given a graph, an independent set is a subset of the nodes where no two nodes in the subset are adjacent. And a maximum weight independent set is an independent set of maximum total weight. So in this example, the value of the maximum weight independent set is 10. In the centralized setting, the maximum weight independent set problem is known to be an NP-hard problem. And even finding an approximation better than delta over log squared delta is hard, assuming the unique Games conjecture, where delta is the maximum degree of a node in the graph. On the other hand, very simple linear time algorithms are known for delta approximation, even in the weighted case. What happens in the distributed setting? So there is a folklore ranking algorithm that gives an expected delta approximation in just a single round. This is also known as the first round of Looby's algorithm for finding a maximal independent set. There is a work by Bopana, Halldorson, and Ravitz in which they show a more sophisticated analysis to the same ranking algorithm that gives a slightly better approximation guarantee. Okay, and if one is interested in approximation guarantee that is not only an expectation, then there is a work by Barry, Huda, Tzenzor, Hillel, Khoury, and Schwartzman in which they show that a delta approximation can be achieved in O of MIS log W rounds, where MIS is the complexity of finding a maximal independent set and W is the maximum weight of a node in the graph. Recall that a maximal independent set is not necessarily a maximum independent set. And this term translates to something like log n times log delta, and this is because W can be as large as poly n, and the running time of finding a maximal independent set is log delta plus poly log log n. In this work, we show that by paying a 1 plus epsilon factor in the approximation guarantee, we can achieve an exponential speedup compared to Barry, Huda et al. And if the value of delta is at most n over log n, then we can achieve the same approximation guarantee even in O of 1 over epsilon rounds. So if epsilon is constant, then this is a constant number of rounds. Following the second result, we were curious to see whether it holds for any value of delta. And it turns out that there are values of delta for which you must spend omega of log star in rounds, even for finding an O of delta approximation. So these are very large values of delta. But today, all I'm going to show you is an O of delta approximation in poly log log n rounds. So this is not quite our best result. In order to achieve the 1 plus epsilon delta, we need to use more techniques. But unfortunately, I don't have time today to talk about these techniques. If you are interested in these techniques, please feel free to contact me or any of the authors. Okay, so now I'm going to focus on the O of delta approximation in poly log log n rounds. And a good way to understand this algorithm is to first consider the unweighted case. And let me denote by G the input graph to the CONGEST model, and by V the set of nodes, and E the set of edges. The first observation to make in the unweighted case is that any maximal independent set contains at least n over delta nodes. So by just finding a maximal independent set, it already gives a delta approximation for maximum independent set. And what is the running time of finding a maximal independent set? So the best current known algorithm runs in O of log delta plus poly log log n rounds. And this is a combination of 3 works. So first, the recent breakthrough by Rozon and Khoury, and another work by Khoury, and another work by Tzenzor, Hillel, Parter, and Schwartzman. So if delta was small, let's say that delta was at most log n or poly log n, then we would be done, right? Because then we can just find a maximal independent set, which is delta approximation for maximum independent set in unweighted graphs. And if delta is at most log n, then this translates to poly log log n. But unfortunately, delta can be as large as n. So the main idea is to sparsify the graph and to find a maximal independent set in a sparse subgraph H. And in order for this idea to work, we need to find the sparse subgraph H with the following properties. First, the maximum degree in H, delta H, is O of log n. And second, the ratio between the number of nodes in H to the maximum degree in H is at least as in G, or at least not very far from it. Okay, so NH is the number of nodes in H, and delta H is the maximum degree in H. How can we find such a graph? So in unweighted graphs, it suffices to sample each node with probability log n over delta. And let's assume that delta is much, much larger than log n. Otherwise, we don't need to sparsify anything. So by this sampling and by using standard Chernoff and union bound arguments, you can prove that delta H is O of log n and NH is omega of n log n over delta with higher probability. Okay? So this implies the second property of the sparsifier that we wanted, which is the ratio between the number of nodes to the maximum degree is at least as in G or not very far from it. And now we can just find the maximal independent set in H, which returns an independent set of size at least NH over delta H, which is an O of delta approximation to maximum independent set in the original input graph G. And since delta H is O of log n, this takes just polylog log n rounds. And that's the whole idea for the unweighted case. For the weighted case, we want to implement a similar idea, but the first challenge is that a maximal independent set doesn't necessarily constitute a delta approximation for maximum independent set in weighted graphs. And this was our starting point in the unweighted case. So to overcome this challenge, we prove that there is an algorithm that runs in MIS time that finds an independent set of weight at least omega of WV over delta, where W is the weight function and V is the set of vertices. And WV is the sum of weight of nodes in the graph. So while MIS doesn't necessarily constitute delta approximation to maximum independent set, we showed that there is an algorithm that runs in MIS time that finds an O of delta approximation. And what is the running time of this algorithm? It's O of log delta plus polylog log n rounds, because this is the best currently known algorithm for MIS. So if delta was small, we would be done. But unfortunately, delta can be as large as n. So we want to use the same sparsification technique that we used in the unweighted case. But now we need slightly different properties. First, we need that the degree of H to be small again, so O of log n, as in the unweighted case. But now, instead of preserving the ratio between the number of nodes to the maximum degree in H, we want to preserve the ratio between the total weight in H to the maximum degree. Okay, so we want WVH over delta H to be at least WV over delta, or at least not very far from it. Okay, so VH is the set of nodes in H. And how can we find such a subgraph H? So unfortunately, the same sampling from the unweighted case doesn't work, and there are counterexamples, but it turns out that it suffices to boost the sampling probability from the unweighted case for a node V by WV, the weight of V over the total weight of the nodes in the graph. And by using this new sampling, one can show using Bernstein and Chernoff's inequality that delta H is O of log n with high probability, and that the total weight in H is omega of WV log n over delta with high probability. And this implies the second property of the sparsifier that we wanted. So now we can use theorem 1 to find an independent set in H of total weight at least omega of W VH over delta H, which is O of delta approximation to the maximum weight independent set in G. And because the degree in H is small, we can do this in polylog log n number of rounds. Okay, so that's all I have for this short talk. There are many details that I didn't cover. If you're interested, please contact me or any of the authors. We will be happy to explain. Let me just summarize with 3 points. First, we find it very interesting that the complexity of 1 plus epsilon delta approximation is exponentially easier than finding a maximal independent set. And this is because a maximal independent set has this lower bound of roughly root of log n rounds due to Kuhn, Moshe Broda, and Wattenhofer. And I apologize if I'm not pronouncing the names correctly. The second point is an open question about the complexity of finding an O of delta approximation deterministically. So there is an algorithm that finds an O of delta approximation in polylog number of rounds, and the question is whether we can do anything better than that. Finally, observe that delta can be very large. It can be as large as n. And the question is whether we can get better approximations. And to get this question to the extreme is how about getting constant approximations? So it turns out that there are constants for which we need to spend at least linear number of rounds or even quadratic number of rounds. And for this, I want to refer to a talk by Yuval Efron as part of the PODC program. And this is the title of the talk of Yuval. That's all I have. Thank you very much for listening.